All right. I believe I've asked y'all this before, and I think the answer is pretty negative. Y'all aren't on campus anytime other than this. Is that pretty much it? Okay, so things going on during the day you're not really all that interested in. Okay. If you would be interested in this one, it's a little bit later in the day. Tomorrow afternoon at the end of Cougars Week, there's a better name for it than that. Cougar Connection Week. They're having a pool party over in the Arthur Shores Fine Arts Building, which also is our gymnasium, which also is where the weight room is, which is also where the pool is. It's further in the back. Nice indoor pool. There's a nice facility there. I'm sure there's going to be great music, great fun, probably food, probably going to be pretty good. So if you want to come and just relax at the end of your day, it's going to be from 4 to 6. So if that fits your schedule and you want to come, I don't think you have to get in the pool. You don't even have to dress for the pool. Just come and enjoy the environment. But you certainly are welcome to do that. Let's see. I think all the other things are daytime activities, so I won't even mention those. Let me mention this one. Oh, he's not here. Okay. I had to do what they call an attendance verification. I did it yesterday, and there were a bunch of people, not a whole lot, but several, who didn't show up on the permanent roll, whereas they've been here all term. And I checked on 2 of them today. They were in my afternoon class, and both of them were fully registered, fully paid, everything else, and yet they're not showing up on the roll. They're in Blackboard, they're in the attendance and everything else, but on the permanent roll they're not. And that's crazy. So they were going to look into it. So there was one person in this class, he's not here, but I don't know his situation at all. But I'm trying to gather data. I'll see the rest of them tomorrow, and we'll find out how many are true and how many are Maybelline. I don't know. Okay. Any questions? Anything we've covered so far? All right. We finished last time, or at least it's my memory and my mark in the book, in the page here, that we did finish 8.3. Okay? And 8.3. That was basically talking about energy and the 2 types of energy, gravitational potential energy and kinetic energy. So it was a fairly short section, just 3 examples, and I think we did all those. Any other questions before we move into 8.4? So 8.4 is going to combine what we just, do you have a question? Oh, okay. 8.4 is sort of going to combine what we did before. Let's see. Thank you. Let me put this in the right place so I don't lose it. Caitlin. Okay. Oh, that was it, huh? Thought I saw her. Okay. Before I lose that, let me get my key. There we go. Thank you. Okay. Back to this. So what we're doing this time is talking about mechanical energy. And I believe I brought that up before. Does anyone recall what mechanical energy is? Mechanical energy, and this is on page 219, very top of the page, very top, very first sentence. Kinetic and potential energy are related to the law of conservation of mechanical energy, and here's what we mean by that. The law of conservation of mechanical energy. The sum of the kinetic energy and the potential energy in a system is constant if no resistive forces do work. So if you've got, and here's the term they use, a closed system, okay? So in other words, there are no other forces involved except the ones that you are identifying here. And the total energy, mechanical energy, which is the sum of kinetic and potential, is always the same. They can flip-flop back and forth and trade with each other as fast as the day is long, but the total mechanical energy is always the same. Okay? But the mechanical energy is the sum of the other two. So, here we have what they call a pile driver. Okay? That thing at the bottom is the pile. Okay? What that is basically the foundation for your building, bridge, or whatever you happen to have. They drive that into the ground as far as they can, and that provides stability for the whole building. Now, in a house, they usually just dig a trench, pour concrete, put some rebar in it, and that's usually enough for a house. The bigger the building, the deeper the pile. The bigger the bridge, the deeper the piles have to be. The less stable the soil is, the deeper the piles have to be. And this is a pile driver, and that's exactly what it's doing. This is a huge mass up here, okay? And the device over there, crane type thing, is lifting that up as high as they can and keep it in the chute. Then they release it, and it falls because it's a big mass falling at a acceleration due to gravity. It builds up a lot of speed at the bottom, and then at the bottom it hits the pile, okay, and drives it into the ground. Okay, Jennifer Addison is here. All right, so half my Jennifers are here now, so all right. So that's the principle here. So basically what we have, now I'm going to add a little bit to it. The crane here is lifting the driver, okay? Let me get my pen activated here. Is lifting the driver up to this point. It's doing work on the driver. The work that it's doing is it's lifting that weight, so the work it's doing is mgh, where that is the h. That's the amount of work it did lifting it. Now, at the top here, this mass here, that weight, mg, has maximum potential energy. No kinetic energy, it's not moving, it's sitting perfectly still. Now, once he releases it in here and lets it free fall down the chute, now they usually have this very well lubricated, so it just goes straight down the chute, and when it does, then it changes its potential energy at the top with no kinetic energy at the top until right before it hits, it has maximum kinetic energy and basically zero potential energy, okay, at the top, at the bottom, okay? So its energy has changed from all potential at the top, no kinetic, to all kinetic and no potential at the bottom. So the energies have gone back and forth. Guess what? Because the mechanical energy, which is the sum of those two, is always equal. Whatever it is at the top, that's what it's got to be at the bottom. So every bit of potential energy you had at the top is now kinetic at the bottom. Every bit of it, okay? Because the sum is constant. Anywhere in between is some kinetic and some potential, but they always add to be that mechanical energy, which is the EP max at the top and EK max at the bottom. That's the total mechanical energy. Does that make sense? Okay. So what it does, that force of kinetic energy does work on the pile and drives it into the ground, okay? And that's how the pile driver works, okay? Now, the potential energy at the top is exactly what I've got here. Is that energy, the work done by the device to lift it up, the crane to lift it up, that's the potential energy it has at the top, mgh. Now this mechanical energy at the bottom, kinetic energy at the bottom where it's the maximum, kinetic energy is 1/2 mv squared. And it really should be a V max squared, but we just don't know what that is right now, okay? Now up here, it's also 1/2 mv squared, but what's the velocity at the top? The mass at the top. What's its velocity? 0. It's not moving. It's being held there. Once it's released, it starts picking up kinetic energy because it starts picking up velocity. So this is 0 at the top because velocity at the top is 0. That's a T there, okay? Okay. Now, at the bottom, this is where your potential energy is 0 because your H is 0 there. That's still mgh, but now the H is 0 at the bottom. So therefore, the potential energy is 0. So what we've got here is the kinetic energy, the potential energy at the top equals the kinetic energy at the bottom because the other two are 0 there. Okay? Let's see if they have the next slide. Yeah, that shows at the bottom where the pile driver hits the pile. Okay? So here the kinetic energy is the max right before it hits. Not when it hits, but right before it hits. And this is, again, 1/2 mv squared. But this is your V max, the maximum velocity it got. Here, this is still mgh, but the deal here, your H is 0 at the bottom because that's where your H was defined from, the top of the pile. So all your potential energy at the top became kinetic energy at the bottom, and that's what drives the pile into the ground. Okay. And because those two are equal, let's see, I don't think they have another slide, no. Okay, because those two pile energies are equal, mgh at the top equals 1/2 mv squared. I'm going to put it as max at the bottom. Okay, this is potential energy at the top equals kinetic energy at the bottom. Okay, now the top. Yeah, at the top. Okay, I just put that in. The book didn't put it, but I put it in. And this H down here is H at the bottom, which is 0. Okay. Now, usually you know the mass. They already have determined how heavy that thing is, what its mass is. You know G, right? Please say yes. What is G? Acceleration due to gravity. Depends on what units you're in. 32 feet per second squared, or 32 point something, 2 or 4. Point what? 2? 32.2 feet per second squared, and in the in the SI system, 9.80 meters per second squared. So we know what G is. You know the height. You can measure that, how high you lifted it over the top of the pile. You know that one. The thing we don't know is how fast it's going at the bottom. Okay? So that's usually the thing we're looking for. What is the velocity at the bottom? Well, guess what? To solve for this V at the bottom, first thing we're going to do is multiply both equations by 2. That gets rid of our 1/2, both sides of the equation by 2. Okay, that gets rid of the 1/2. Next thing we do is divide both sides by m. And looky there, the m disappears. It doesn't matter how big the mass is or how small the mass is, it doesn't affect the velocity. Now, it affects how much it drives it into the ground, of course, because even at a high speed, a low massive thing is hardly going to make any difference at all. But the speed doesn't depend on the mass. So what we have then is V squared is equal to 2GH, and the H is at the top. Well, we don't really care what V squared is. We want to know what V is, what the speed is. So we take the square root of both sides, and that gives us V is equal to square root of 2GH. Now, did we run into that before in an earlier examples? I can't remember. Did we? Yeah, okay. So there's usually how we calculate our velocity at the bottom. where v is velocity or speed at the bottom. G is either 9.80 meters per second squared or 32.2 feet per second squared. And the h is the maximum height above the reference plane, which is the top of the pile that your pile driver was resting at. Okay? That leads us to example 1. Top of page 220. Okay. Now, I think we've got white space on this that we can probably work it here. A pile driver falls freely from a height of 3.5 meters above a pile. So there's our height. That was where it fell from, so that would be your maximum height. So we'll say the h is 3.50 meters. Now, just to get an idea what we're talking about there. Okay? I'm about 2 meters tall. Okay? And then from my head to the ceiling is about another meter. Okay? So that would be 3 meters. So then go another half meter, which would be about this much further. And that would be about 3.5. And you have a huge mass there falling that distance. I don't want to be under it. Okay? At all. Okay? So don't have it on top of me. Okay? Now, above the pile. What is the velocity as it hits the pile? So what we're looking for is v. That's the unknown here. Notice we don't know the mass, but we don't need to know the mass. This formula here takes care of everything. So what is v? What is v? The square root of 2gh. Okay, I don't see a g anywhere here. What in the world is g? Is what? Yes, because we're in the metric system, this is in meters. Okay, so it's 2 times 9.80 meters per second squared times, and what's the h? 3.50 meters. Okay. Now, do any of you have any deep-seated worries about that 2? Yes, what about it? Okay. You know where it came from? When we multiply both sides of the equation up here by 2 to get rid of that denominator. That's where the 2 came from.
Okay, I know this is 8.1. Are we supposed to do that for the same thing at 8.3?
I think we had some very similar to this.
It confused me. That's what it did on 8.3. But see, it was, you were doing, that was number 3.
Yes.
That if I'm not mistaken.
Yeah. I'm sorry. I'm sorry to go back.
No, you mean in the
I tried to do that with number 3, but I was doing it totally wrong because it didn't work.
in the homework exercise?
Yeah. Because it kind of reminded me of that.
Okay. The thing is there, you're not looking for V. They gave you V.
Yeah.
Okay. But there you're looking strictly for kinetic energy.
Yeah.
So in that one, since we mentioned it, all you use is this formula right here. 1/2 mv squared. That is your kinetic energy. That's all. And you got the mass, and you got the velocity, and you got the 1/2. Is that the one you meant?
Yeah.
On page 217? Yeah. Now, there may have been some later ones that you did something similar, like example 2, example 3 at the top of the page. Is that what you were talking about? Or you were talking about the problem set at the bottom?
I was talking about the problem 3. That one just kind of threw me off.
Okay.
I see what you're talking about on example 3 at the top of the page.
Yeah, that is a different one, but it's still got a square root in it, but it's a little bit different. Let's see if we had one that was more similar. I think I may have introduced it to you, but I don't think the book did yet. Okay? I teach several different classes, and sometimes I can't remember which I've taught in which class. But this is all we have here. Okay? So pull out your handy-dandy calculators. Now, depending on the type of calculators you have, you might just start with the square root key, and if that opens a parentheses for you, then you type in a 2 times, oh, my question a little while ago, I was worried that some of you might be very concerned that 9.80 has 3 significant digits, that 3.50 has 3 significant digits, but how many does 2 have? 2 is a pure number, and you could put it 2.00000000000, as many zeros as you want after it, it's still 2. That is a pure number. It's not a measured number. These other things are measured. You measure your acceleration, you measure your length. All those are subject to error. This 2 is a 2, pure 2. 2, as many decimals as you need. So don't worry about that. That doesn't count in your significant digits. Count that as many zeros as you want. Okay? So, if you got your square root key, if that opens a parentheses, then do 2 times 9.8 times 3.5, close parentheses, equal. That should give it to you. Now, if you have calculators like I used to have, I don't have it anymore, you have to multiply the 3 things together, hit equal, and then take the square root of the answer. Some of the older calculators do that. You have to know your own calculator. And if you have any questions about it or problems with it, let me know. I've used enough different kinds of calculators, I can probably help you figure those out. Okay? But you need to know how to do yours. Has anyone done the math? What do you get? 8.28. That sounds like the right number of digits. Now, notice the units. We have meter times meter, that's meter squared per second squared. But when you take the square root, you're also taking the square root of the units, so that gives you meters per second. And that's a great unit for a velocity. 8.28 meters per second. And that's what the book got to. Good for them. Okay? See how that works? All right. Now, pile drivers it works with. There's another device it works with. Anyone know what that might be? Did you say a wrecking ball? Yeah, it could be either one. It's a pendulum. And it can be a wrecking ball or it can be a very sensitive clock pendulum, like in a grandfather or grandmother clock, that thing that goes back and forth. That is a pendulum, okay? And here's the deal, folks, on the pendulum. If this is raised as high as it's going to go, okay, then, and it's at rest here, then your potential energy is at its maximum. If it's at rest, it has no kinetic energy. But when you release it from there, it's going to follow an arc downward, right? Okay? And when it is going down, the potential energy is decreasing, but the kinetic energy is increasing until it reaches the bottom down here, and guess what is happening then? Maximum kinetic energy and 0 potential energy. Okay? The reason for that, that's as low as that can go. That should be where you measure your potential energy from. How high do you think it's going to go on this other side? Up here, down here, where do you think it's going to go? It's going to go to the same level or awfully close to as it was there. Why? Because as it goes back up, now it's losing kinetic energy, gaining potential energy, but the total mechanical energy is constant. And it can't go any higher, because then it would have more potential energy than it ever did before. And it can't, if it went any lower, that would have to be because of friction, but we're going to assume that this is awfully close to frictionless. Okay? So let's think about that grandfather clock again. You have seen them before, right? What do you notice about them, especially the pendulum? Yeah, they go back and forth like this, okay? So what?
She says persistent.
I said persistent. Yeah.
It's not pro, I'm sorry.
Says what? I couldn't hear.
It is consistently.
Yeah, and it goes back and forth and back and forth. And that's because it's constantly maximum potential, maximum kinetic, maximum potential, maximum kinetic, maximum, yeah. It's going back and forth like that all the time. Mechanical energy is constant, stays the same. But tell me a little bit about it. Doesn't it look really big like this in front usually? But if you look at the edge, very thin, because it's going back and forth. The thinner it is, the less air resistance it has. So it's meeting very little air resistance. This thing like this, it's not going back and forth like that. It'd be a lot of air resistance, but it's going back and forth like this, so very little air resistance. And then what are usually built in? A glass case, aren't they? And that's so you can see it and appreciate it, but it's also so wind and things like that can't blow on it and mess it up. So that's also minimizing its air resistance, okay? So yeah, there's a pendulum. And it goes to the same level on this side, it is on that side, it is on this side, and goes over and over and over again. But all those clocks, you do have to wind. And why? There is a little bit of friction. Anytime you hear a tick, there has to be friction that makes that tick, okay? Ticks don't come out of nowhere. Something has made a noise, okay? So that uses a little bit of energy. So that's why you wind the clock, to give it just that little bit of boost to get it back to that same level every time, okay? We won't worry about that now. We're going to assume this is a frictionless peg up here. No friction whatsoever. Okay, so that's your setup for your pendulum. Conservation of mechanical energy, also used right here. Let's see if they have another picture. Yeah, here's one. When you released it up there from the highest point where the potential energy was max, then it went down. Let's see, I'll do it on this side. It went down until it's, say, about halfway, and there you have equal kinetic and potential energy. Still has some potential energy because it has further it can fall, but it's gained some kinetic energy, but not as much as it will get. Okay? Then you let it fall a little further, and now all of the kinetic energy, the mechanical energy is kinetic energy, zero potential energy, because that's as low as that ball can go in this problem. As low as it can go, so here your H is 0. We call that the zero reference frame. Up here, the H was the maximum. You can't get any higher than that. That's where you released it from. It'll never go higher than that because that's the maximum potential energy. Okay? And the same rule holds that we saw before. Here it's gone over here. The kinetic and potential are the same here, and they're the same here, but here the kinetic is 0, potential is max. Down here, the potential is 0 and kinetic is max. Okay? And again, because mechanical energy is the sum of the potential and kinetic, that potential at the top has the equal kinetic at the bottom, because the others are 0 at those two places. So the same formula held that held before about the velocity. So I think we're ready for example 2. Drop a 5.000 kilogram mass from a hot air balloon at 400.0 meters above the ground. This is not a pendulum problem, okay? So, let me see if I can find some picture to write on. Tell you what I'm going to have to do is get out of that, discard that, and get this one open. Sorry about this, I forgot to do this at the beginning. The last summer when I taught this course, I had a student who sat right up here. She made sure I had this open every time. She didn't like me writing all over the crowded thing. She would say, "Have you opened that?" Okay, why did Blackboard? That was the wrong thing. That's not what I wanted. Okay, this is the one I wanted. I don't know where my brain was. I was talking, not thinking. Oh, me. Sorry. Why is this taking so long to open? Let me try it again. And now it opened twice. Good for it. Okay. No, it didn't. Sorry. I thought it opened twice. That was the other one back there. Okay, here we are. And we'll go from this one. All right. And slideshow at the beginning, our current slide. And let me get my pen activated to black. Okay. Okay, we have a hot air balloon. Okay, here's the ground down here. Okay, we have a hot air balloon up here. Here's the basket. And here's the balloon. I'm not going to draw all the balloon that's up here. And you're in the basket, and you drop a 400 kilogram, no, 5 kilogram at 400 meters, 5 kilogram mass. Okay, so here you drop a mass, and here's the mass of 5, sorry. I'm talking faster than I'm thinking or something like that. Okay, here's the mass, and it's the mass is 5.000 kilograms. Okay, you're dropping that out of the basket. Okay, and you are .0 meters above the ground. So that's your height. Okay. Find the kinetic energy, potential energy, and the sum of the kinetic and potential energies in 1 second intervals until the mass hits the ground. Assume no air resistance. Ooh. What's one piece of information we don't have yet? But you know it. Don't have to have it. We'll get to it. Okay, what are we looking for? Find its kinetic energy. So we're going to be doing KE. They call it E sub K. I'll try to remember to do that. I like KE better. KE. What's its formula, by the way? 1/2 mass times velocity squared. Perfect. Okay. Find its potential energy. What's the E sub P? Is what? mgh. Perfect. Okay. Now this is H max. Let me put the max here. Okay. Maximum height. Okay. Is potential energy, and the sum of kinetic and potential energy. What do we call the sum of mechanical and sum of kinetic and potential energy? You got it. Okay. E sub m for mechanical energy is E sub k plus E sub p. Right? Okay. Until the mass hits the ground. 1 second intervals. Okay. Now, we got to do something else, don't we? You got to somehow figure out the velocity. Okay? So we're going to have to use some of the kinematic equations that we had before. Okay? We got to do two things. Get the height at various times, and they call this S. So this is S max. Okay? How far it fell. Okay? And we're going to need to know the times. No, well, we're going to pick the times, 1 second intervals. We're going to need to know velocities at each interval. Okay? So we need the distance, velocity, E sub k, the height, okay, we'll get that in just a second, and then the E sub p, and then the total. Okay? Now, we'll start at t equals 0 seconds. Okay? At 0 seconds. That's right here. You're holding it up there right before you've released it. The first thing they look for there is the distance that it's fallen. So I said this backwards over here. Let me erase this. Your S is how far it's fallen. So the H is going to be how far it has left to fall. You see that? How far it is above this. The ground down here is your 0 reference level. So this is where H is equal to 0. So what is your H up here? That's your H max, 400 meters. So when it falls, the distance it's fallen is S, and the distance that still has to be, that's your H. So the H is going to be, this will be the S, and this will be the H. So what do we notice about that? The distance that it's fallen, if we can calculate that, the H is going to be 400 minus that. Because the total height there is 400, right? And if you subtract the distance it fell from 400, you got what the new H is. So that's how those two things in the table are going to be. So you got T equal 0. Next thing we're going to do is S. Okay, then we're going to do V. And then we're going to do E sub k. Then we're going to do H. Then we're going to do E sub p. And then we're going to do E sub m. They call it total. I call it mechanical energy, which is the sum of kinetic and potential. So, what is your S? How far has it fallen right before you release it? Has it fallen at all? No. So the S at t equals 0, your S is 0. What is your velocity then? Right as you release it, what's its velocity? 0 also. What is kinetic energy then? Zero, because the velocity is 0. What is the H then? That's the 400 meters, right? 400.0 meters. What's your potential energy then? Well, let's see. Did they tell us the mass? Yes. The mass was 5.000 kilograms times G of, whoa, what's the G? 9.80 meters per second squared. And what's the H? 400.0 meters. Okay? Now, 400 times 5 would be 2,000 times 9.8. Anyone got it? 2,000 times 9.8. 19,600. 19,600. Does anyone know what units that is? The kilogram meter squared per second squared. The joule, excellent. That's in joules, okay? And what's your mechanical energy? Yes, it's the sum of the kinetic and potential, which is 19,600 joules. Now, they do something in the book I find a bit strange. Okay? they put a bar over the first zero there. And I'll admit that the mass is four significant digits, and that the height is 4 significant digits. But guess what? Your G is only 3. So how in the world can they give you 4? They sort of messed up there a little bit, okay? Let them get by with it. Give them a break. They don't always get everything right. But it doesn't really matter. 19,600 joules. That'll do. Okay? At t equal 1 second. Okay? How far has it fallen? Now, here's where you have to go back to an earlier equation. I don't know if you remember it. This is from chapter 5. That's S is equal to 1/2 AT squared. You remember that? How far it fell was 1/2 AT squared. Where the A here is actually acceleration due to gravity, so you can put GT squared. Okay? Now, remember we said that's the simplest of the form. That's when the initial velocity is 0, which it is, and the initial displacement is 0, which we're going to count it as being 0. And how far it falls will then be added to that. So if you put in 1/2 of 9.80, and then 1 squared is 1. Okay, and this is meters per second squared. I forgot to put this in. The second squareds go out, and you're left with 1/2 of 9.8, which is 4.90 meters. Right? Everybody agree? Now, what is the velocity there? Well, if we go to that same set of formulas, remember V is equal to V A times T, and here the A is your G, so G times T, that's 9.80 meters per second squared, I can't write, times 1 second. 1.00 seconds. You got the clock. You can do it as much as you want to. That would be 9.8. And see, 1 second cancels out one of those, and you're left with meters per second. So that would be 9.80 meters per second. Now, with that as a velocity, you can calculate your kinetic energy. How do you do that? Your formula up here, 1/2 mv squared. So 1/2, the mass, 5.000 kilograms, times velocity squared was 9.80 meters per second squared. No. Yeah. No. I put acceleration. No, that's right. Meters per second, not meters per second squared. This one's a meters per second. Okay. 1/2 of that. Okay. Not squared. Okay. And here you get kilogram, meter. Oh yeah, you square this. I'm sorry. You square that.
So you matched it, first the square, you said the x to the second power at the end.
Okay, say that one more time.
To get the v squared.
V squared, yeah. This V right here, we're squaring it. And I forgot to say that, yeah. Yeah, I said it, but I hadn't written it down yet. It's 9.80 meters per second. See, I said meters per second squared, but I put my second squared down there. It's meters per second, the whole unit squared. The squared goes up there now. And it's 9.8, which I'm used to saying is meters per second squared, but that's the acceleration. That's not what I'm talking about here. That's meters per second, that whole quantity squared. So, if you got a calculator, 1/2 of 5 times 9.8 squared equals 2.5 times 9.8 squared, What do you get? Say again, 210? Is that what you said? Okay, 240, is that what you said? I'm not, huh? Is that what you said? 240 joules. Okay, we'll just, okay, I bet you in the book they put it, no, they just do it 240 joules. You got it right. Okay, what's the height? Well, if it fell 4.9 meters from 400, that would make it 395.1 meters, right? Because it fell almost 5 meters, so it had, the height was now 395.1. Okay, potential energy, mgh, that's the mass, 5 times g, 9.8 times 395.1. Okay, it's mgh right up here. Your mass is 5, okay, times g is 9.8 meters per second squared. That's the meters per second squared. And then the h is this one, 395.1. Anyone got it? Going to be pretty close to what it was, but it's going to be off a little bit. I'm going to guess about 19,360 or something about like that. Anyone get it? MGH, 5 times 9.8 times 395.1. The math is not that hard. What you get? Ooh, say that one more time. 109. Okay. This, okay. 19,360 joules. Let's see. Yep. Looks about right. And then if you add the kinetic plus potential, what do you get? Take that 19,360 you have there, add 240 to it. Add 240 to it. Guess what? Help me, help me. 240 plus 19,360. 19,600. Look at that. Mechanical energy did not change. Okay?
That's when I got confused, but I remember now you say that it's okay.
Yeah. Okay. That was so much fun. You want to do 2 seconds? At 2 seconds, we go back to our S here was 1/2 GT squared. So that's 1/2 9.8. Okay. Wait, yeah. 9.8 times 4, because 2 squared, wait, I'm sorry. Yeah, 2 squared. So it's 1/2 of 9.8, which is 4.9 if you want to just write 4.9 times 4. 4.9 times 4. You got the 4 by the 2 seconds squared. 2 squared is 4. So what's your S? 19.6 meters. Okay. Now your velocity. Do the same thing as we did before. 9.8 times 2. 9.8 times 2, GT. Now we're doing 2 seconds, so it's 9.8 times 2. I think I can do that in my head. 19.6 meters per second. Okay. What is your kinetic energy? Remember kinetic energy? 1/2 the mass, so that'd be 2.5 times the velocity squared, 19.6 squared. So 2.5 times 19.6 squared. 950 joules.
660.
960?
Yeah, 60.
Okay. 960 joules. Okay. What was the height now? If the distance fallen was 19.6, you subtract that from 400, and you get 380.4, right?
What did we subtract again? You said, I'm sorry?
You subtract it from the 400 because your S plus H is equal to 400. So subtract the 19.6 from 400, and I hope you get 380.4. Do you? I may be doing it wrong in my head. Don't let me do it.
No, that's right. I was just wondering what was you subtract. I got you. I'm back on
Got it? Okay.
Yeah, that's great.
Okay, now that you've got your H, you can calculate your EP, MGH. So M was 5 times 9.8 times that number right there, 380.4. Five times 9.8 times 380.4. 18, 679. Let's just leave 679. Let's just leave it 680.
It
Okay.
would actually be 640. Yeah. So
Oh, 640?
640, yeah.
Okay. 640. I can't. Where's my eraser? There it is. All right, 640. Ooh, where's my eraser? Pen. 640. Okay, joules. Now let's add your 960 to 18,640. Add your 960 to 18,640, and what do you get? 19,600 again. All right. My other Jennifer's here. Okay. Good deal. All right. Do you see how to do this? Okay. And sure enough, your kinetic energy is increasing because the velocity is increasing. Your potential energy is decreasing because your height is decreasing, but your mechanical energy is always being the same. This is example 2 on page 221. We've done the first 3 lines out of that table. Yes?
Just have a quick question. The equations, we start with V, the velocity equals, this that says AT on it. Is that what it says?
Yeah. Okay. Let me clean those up a little bit so they are easier to read. Okay. All right. Now this is in no particular order. It's just the order that happened to be over here. Okay. All right. Your E sub k, that's the one that was here, is equal to 1/2 mv squared. Okay. Yes.
She want to know about the V.
Yeah, I know. I'm getting there. Okay. I was just cleaning them all up while I'm getting there. Okay. This one right here, I think that's the one you're asking for. That's V is equal to AT, which is also equal to GT, because your acceleration is the acceleration due to gravity. And then I'll take out this and, ooh, I just erased something. Okay. So, okay. I'm going to do it maybe a little bit more organized. Is that possible? Okay. All right. I'm going to try to get it as much as I can over. Where did you go? There you are. Because the S is equal to 1/2 AT squared, which is 1/2 GT squared, the acceleration due to gravity. So that's where we're getting that from. Okay? Your V, let me erase some more here. Okay? Your V here, these are from chapter 5, hopefully. V is equal to AT, which in this case is GT. That's your acceleration due to gravity. So that's how you're calculating your V. Okay? Now, I started to write them here because we had more white space. So I thought it's going to make more sense if they're over here. Actually, here it is right here. The E sub K is this one right here. 1/2 mv squared. Okay, your H. Your H is equal to your total height, which was 400.0 meters minus whatever your S was, how far it fell. So that's where that came from. Okay? Then your E sub P, I'll take off, I wrote them in so you could see me do that the first time, but now that's your MGH right there. And E sub M is the one I just erased, and y'all remember that one, right? E sub M, which is mechanical energy. The book doesn't use that terminology, but I do. And that's equal to E sub K plus E sub P. Basically, those two columns there. And that's your E. Is that helpful?
Yeah.
Okay. Makes it a lot neater. You don't see my numbers in there, but now that we've done a few numbers, I think you can put your own numbers in. Right? All right. You want to see one more, or you're happy with that? We can take T equal 3 or any T that you want. Second? One more. Which number you want? How many seconds? 3 or something bigger? 3? Huh? 4. Okay, let's go to 4. T equal 4 seconds. Okay? What is your S then? Okay, remember what the G is? 9.8. Half of 9.8 is 4.9. 4.9 times, in this case, it's going to be 4 squared. So 4.9 times 16. (4.9 × 16). Say again? 78.4 meters. That's how far it's fallen. Okay, at what velocity? Again, your G is 9.8, and your T is, in this case, 4. So 9.8 times 4. Say again? 39.2 meters per second. Okay, because T times is in seconds times meters per second squared. That gives you meter per second, an excellent velocity. Now your E sub K. Your mass being 5. So 1/2 of 5 is 2.5 times your 39.2 squared. 39.2 squared. 2.5 times 39.2 squared. Anyone got an answer yet? Two 2.5 times, say again? 3,841 joules. Okay, let's see. Okay, yeah, they rounded to 40, but that's okay. We'll be happy with that. Okay, what's our H? The 400 minus the S. So that's going to be 321.6. I'm doing it in my head, so you correct me. Is that right? Okay. And then your E sub P, which is MGH. M is 5, G is 9.8, and H is 321.6. Okay, say that a little bit louder.
15,760.
760?
Yes.
Okay. Now, let me just give you a hint. They are going to leave that as a 0 there, okay, not a 1. So add the mechanical energy is the sum of kinetic and potential. So that's 3,840 plus 15,760. What do you get? 19,600. How in the world did that happen, folks? Yeah, mechanical energy is conserved, always constant. So you see how you can fill up the rest of the table. If you do it, you're probably not going to forget that distance formula for very long, or the velocity formula for long. You're going to have them drilled into your head. So do as many of those as you'd like. Notice the kinetic energy is increasing as it falls. The potential energy is decreasing. They happen to stop it at 9.035 seconds, because at that point it's right as it's landing, and then it's all kinetic energy, 0 potential energy, and the total mechanical energy is still the same. Make sense? Yes?
I'm sorry, I got you and you may have covered this.
Okay.
I just have a quick question. When one is figuring out the kinetic energy formula, 1/2 times mass velocity squared.
Right.
Is it correct to actually do the exponent first in the order of operation?
Oh, okay. Yeah.
Is that important?
Okay. As long as you see, when you're an exponent, really what you're doing is multiplying a number by itself. So as long as you're multiplying, it really doesn't matter, okay? Now, what you don't want to do is do 1/2 the mass times velocity and square the whole thing. That's not what you want. You want to make sure you're only squaring the velocity part.
So is it correct that you would typically square the velocity?
You can do it that way, then multiply by mass and take half of it. That's perfectly fine. You'll get the same answer.
Order is important. To make sure that you're
Yeah. Okay, yeah. When you think of, please excuse my dear Aunt Sally, okay, and you got the parentheses first where we don't have any, then you have the exponents. That's really important when it comes to more of the Aunt Sally part, the addition and subtraction. You've got to do the exponents for. We see multiplication and division. The squaring, the exponent, is really just another multiplication. It's just multiplying the same thing that many times, 2 times for a square. So it doesn't matter as much with multiplication. If you are adding something, by all means, you've got to do that exponential, then the multiplication division, before you do adding or subtracting. So yeah, it's most important then. So it's not a bad practice to always do the exponent first. You'll get the same answer, the correct answer.
Calculator, it's going to automatically do it because it understands that what's next to is what is actually multiplied.
Right. Now, I say that, but some of the older calculators, especially the cheap ones, I've got a little cheap one that was given away by somebody years ago. It's still working. I don't believe it. I've gone through so many scientific calculators that I've had to pay for if someone's given to me or something like that. But this little cheap one that was free, they were giving away at a table, it's still working, okay? I've been through like 3 scientific calculators. But that one doesn't obey the rules of order of operation. It does whatever you tell it to in the order it tells it to. So When you multiply and it gives you a number on the screen, then you square, it's going to square the whole number. So you have to be careful, especially those cheap ones. You can't trust. You get what you pay for, okay? So watch those. But on most of the good calculators like this, yeah, it does what you tell it. Okay, now, I hesitate to agree too rapidly with that because I'm trying to think of a good example now. Especially when you're dividing, okay? And I can't think of one that we would be doing, but let me make up something. Like if you were looking for something that's equal to, let's just say, 1/2 mv squared divided by, I'm just making stuff up so this won't be, mv plus GH. Okay, I just made something up. Nothing's going to make sense in this problem. If you do this the way you're saying, 1/2 mv squared divided by mv plus GH, you're going to get a totally wrong answer. Because here's what the calculator is doing. Okay, yeah. Here's what the calculator is doing. It's doing 1/2 times m times v squared. It did that right. Then it's going to divide by m, and then multiply that answer by v, and then add to that answer g times h. No, that's not what's happening there. So anytime you're dividing, especially a long division line like that, you have to understand that what you've got down here is parenthetical. That's in parentheses. If you put the parentheses in, mv plus gh, it does that right, close that parentheses, then hit enter, then it does it all right. Does it all fine. But you have to put those parentheses in there. And you just have to know when to do that. And anytime you have a group like that, you understand that's what you're doing. It's that thing squared. Not squared, grouped together. So that's not what this problem is, but I didn't want to agree with you completely until I explain. There are exceptions to it because
so the order of operations is important.
Is very important. And you see here that you have to consider to be parenthetical. You got to do it first. Okay? And you don't have to write it down separately, but you could do that first, then do 1/2 mv squared divided by, and then plug in that number. And that is important. So you do have to watch that. And you have to know your calculator of whether it's going to do those order of operations properly. Most of the good ones today do. They recognize it. But they can't tell what you meant by the other thing because it's doing exactly what you tell it to. So you have to put it in the parentheses because they belong there, though you don't always write them there. All right. Did you need to see any more of those done? Okay. Thank you. Okay. No, y'all were getting them done really fast, so that's great. All right. Now let's go out of this. All right. And go back to this one and advance it 1, 2. Here we go. You think that probably roller coaster rides and things like that are all for fun. No, they're full of physics, okay? That's exactly what makes them fun. Because really what's the exciting part is not how fast you're going, but how much you're accelerating. It's the acceleration that you sense, okay? Have any of you ever been in a jet plane? Okay, sure, most of us have. How fast do they typically fly? 500 miles per hour. That's pretty fast, okay? But do you notice that when you're sitting in the jet plane watching your movie or reading your book or something? You don't notice that. It's only when you accelerate, as in suddenly you change elevation really fast. like you hit a weather disturbance and you drop. You notice that because you now have gone suddenly downward very quickly. That's an acceleration. The speed itself is not. It's getting to that speed or changing the speed. That's what's the exciting part, the acceleration. So the work is done, and here's your zero reference level down here. If I can get my pen back. Down here is your zero reference level. And you had to, and sometimes they have a little device or a pulley or something like that that literally is pulling the roller coaster up to its highest point, P. And then maybe it gives it a little shove, but it gets out of the way and gives it a little shove. And from there on, it's on its own. So here it has maximum, well, same type thing. Maximum potential energy here, zero, well, almost zero kinetic. It may be moving very slowly. But when it starts going down, it's picking up speed very quickly, right? And that's when people start, and that kind of stuff. Yeah, and picking up and increasing kinetic energy because that depends on your speed. So you're increasing kinetic really rapidly, and then when you get down here to the bottom, that's when the other scream happens because you've been accelerating downward here. Now you're changing not just speed, but you're also changing direction, which is acceleration, and you do the dip. And that's where you tend to throw up. No, I mean, that's where you feel like doing that. That's where the stomach, you don't know where it's going to end up, okay? And then you slow down going up and you're feeling a little better. And then you crest the top and you have another dip there and another. And now you're changing direction as you're increasing speed. And that's exciting. And people scream and throw their arms around and then make their way on down and you stop somewhere at the bottom. Okay? It's the acceleration that's the exciting thing, when you're changing your speed. But that's all dependent on mechanical energy. The sum of kinetic plus potential energy. Every time you go up, you're losing kinetic energy, gaining potential energy. Every time you go down, you're losing potential energy, gaining kinetic energy. Mechanical energy is constant throughout. Okay. Now, a lot of times, they'll put the starting point up at the top, so they don't have to pull anybody up there. And hopefully you make your way back there, somewhere near the top. Probably not right at it. Maybe down here somewhere, and then they pull you that last little bit, and you go that way, you certainly come back up. Okay. Now, how about this one? That really gets some screams, doesn't it? Okay? If you started at the top, now, this looks like it should be a problem, but I don't see it in here at all, okay? Oh, there it is. It's Applied Concepts on page 229, okay? If you really wanted to get some practice doing that, there's a good place to do it, okay? So if you really want to do that, that'll be at the end of the chapter. And you'll really put a lot of stuff together there. And you can figure out the velocities and energies and everything that you need at every point there. A, B, C, D, and, oh, they don't have an E. Okay. If you want to do that, we can later. All right. The sad news is they're skipping some things here. All right. Now, so let me go back, and I hate to do this again, but let me get out of that and go back to this one. Okay. Here's a couple of other issues here. Okay. Oh. Yuck. Let me go back, sorry. I see now there were some letters on this one I didn't pay close attention to, sorry. what they're saying here at point P, I could leave it red, but I'll go back to black. I think I'll go back to black, yeah. At point P here, they're saying you're at rest there. So your KE, I'm sorry, I like KE. I'm going to put it that way. KE at P is equal to 0. So your PE at P is the max. I don't know what it is, but it's the maximum amount. And that's also the sum of those. This is also your ME at P, mechanical energy at P. Down here at Q, okay, you've got some kinetic energy, definitely, okay? It looks like quite a bit of kinetic energy. But you still have some potential energy. This is at Q. Potential energy at Q. And they don't say how much, but that's what your potential energy is there. I mean, depending on your height. And they don't give you any heights here, so they just say the height at Q. So this is 1/2 mass times velocity at Q squared plus mgh at Q. Okay? That's your mechanical energy here, me at Q. But guess what? That's the same as the me at P and the me everywhere else. This is 0 here. Here is your mgh max. However high you are there above the ground level, 0 reference level, that's your H max. Okay? Then you can follow the rest of it, but down here at R, guess where you are at R? Where you are at R? Okay, repeating. Your potential energy down here at R is 0 because you're at the 0 reference level. Your height is 0 there. Okay? Now your kinetic energy at R is your max. And of course the mechanical energy is the sum of those two, and that's the same as it was everywhere else. Okay? Equal to there, equal to there. Okay. They wanted those put in, so I put them in. And this is 1/2 mv. Here's your maximum velocity here, squared. Okay, they put R down there, but that happens to be your maximum velocity squared. Okay. All right. They had that written under the slide. I didn't notice the P. I saw the P. I didn't notice the Q, or didn't really pay attention to the R either. But that's what they wanted to do with that. Okay. Now we go back to this one where we were before from current slide. Okay. Now, we're not going to do a whole lot with this, but just so you get the idea that it's in the text here, we have several types of collisions you can have. Okay? And I'll give you a couple of really dumb examples. Let's say you had, any of you remember silly putty? Okay. Silly putty was this mess you could play with and stuff like this, and you could throw it against the wall, and it would generally just splatter against the wall and stick there, wouldn't it? Okay. That is called a totally inelastic collision. There's no rebound. It just against the wall. Some people say that's how you test and see if your spaghetti's done. Throw it against the wall. If it sticks, it's done. I don't do that. I like to eat spaghetti. I don't like to eat off the wall, so never mind. So I don't like to waste food, so unless it goes to my waste, that's fine. Okay. But anyway, that's inelastic. The opposite of that is a totally elastic collision. And think of, any of you play pool or billiards? Okay. Those balls hit each other and they bounce completely. There's no deformation. They bounce completely. They should do it off the sideboards too. Sometimes they're a little soft and don't quite do it as well. But the game of pool is based on pretty close to elastic collisions. The reason I say pretty close to and not including, you hear the sound when they hit, you know there's some energy lost due to that. So that's not totally elastic, but it's pretty close. So in an elastic collision, okay, whoops, let me get my pen back. I keep having to change every time. In an elastic collision, okay, the total kinetic energy, I'll do it E sub K, I'm just going to write it, is conserved. Meaning the kinetic energy before the collision is the same as kinetic energy after the collision. Total kinetic energy is conserved. That's not the case for inelastic collisions. If you have any deformation, bending, busting, anything like that, it doesn't work. But for total elastic collisions. Now notice, remember elastic collisions, those pool tables have to be perfectly level. You don't want them tilted, otherwise their balls always roll to one end and stop, okay? So you don't have to have them perfectly level. You don't want any other outside forces there. Now, in all collisions, elastic, inelastic, pretty much the mechanical energy is conserved. We've just been doing that. Okay, but even more so, the total energy has to be conserved. Energy cannot be created nor destroyed, so the total energy is always conserved. Mechanical, more so in all collisions, but only in elastic collisions is the kinetic energy conserved.
So when you say conserved, do you mean saved?
Stays the same. In other words, the kinetic energy at the beginning is going to be kinetic energy at the end. If you have inelastic collisions, no. Kinetic energy is not conserved. Mechanical energy may be, but not kinetic. Okay? Because always in an inelastic collision, you have some type of potential energy coming into the picture. Say that you have a rail car. If those were bumper cars, this one hits this one, they bump away. That's going to be elastic or pretty close to it. If it's a rail car and they have things, this is going to hit and then both of them move. That's not going to have conservation of kinetic energy, but the total energy will be conserved, but not kinetic. There's another quantity that we talk about a lot in physics, but we're not going to do any, called momentum. Momentum is similar but not the same as energy. Linear momentum is generally conserved in all collisions. Kinetic energy only in elastic collisions. So total energy is conserved, but also momentum. And if you think you've heard me say the word before, remember back when I talked about Isaac Newton, when he wrote his Principia, the principles of motion, he talked about the quantity of motion, which is the product of mass times velocity. That's what momentum is. And there's a lot of things momentum does, energy can't do, because it's a great quantity to deal with. Okay. I don't think they do any examples with that, so that was just in the text in case you need it.
Is momentum a force?
What's that?
Is momentum a force?
No, it's not quite. What momentum is, remember Newton's second law, we say force, and that's a net force, is equal to mass times acceleration. But acceleration is change of velocity per change of time, right? So it's mass times that. Okay? Well, this is mass times a change of velocity is a change of momentum over a change of time. So a force is the time rate of change of momentum, or that quantity of motion. So it's sort of like distance, the time rate of change of that is speed. Time rate of change of velocity is acceleration. Time rate of change of momentum, that's what a force is. So it's a
measure of force?
Not a measure of force. It's the quantity that when you change the quantity over a given time period, that's what a force is. So it's related to a force, but not the same. Similar in that they both are vector quantities, whereas energy is not a vector quantity, it's a scalar. But you don't need to know that for this course, but it is an interesting concept. Now, they have a little thing on backyard physics, and I don't know if any of you have ever played croquet. You have, okay. I can remember playing it as a really young kid. My dad got a set of them, and we managed to lose things really quickly, so we never played them very long, but we played for a while, and my older brother was just way too competitive and would get mad so easily, so we decided to keep the family at peace. We wouldn't play it much more. But anyway, you use a lot of conservation of elastic collisions there. Croquet balls are very hard and they bounce. The trouble is they're on grass, and you lose a lot due to friction, so it can't be that. Now, there's another physics connection that's pretty interesting. Landing on an aircraft carrier, and they have a picture of this on the next page. Both the landing and takeoff are pretty interesting because you have to have a enormous change of energy in a very short time and distance, okay? And so how they launch aircraft on an aircraft carrier is they rev those engines to maximum full throttle. I mean, they're blazing blue flames out of the back of those jet engines. So they're gunned as hard as they can be. They're on what is called a catapult, which the steam-driven thing that throws them off the end of the ship while they're gunned at max thing. And even then, they tend to dip, and they come awfully close to the water, but then they rise on and go. I know because for a few months, my bunk was at the back of the jet blast deflector just below the flight deck, and I heard all those night operations every time they launched them. Well, until finally I'd be so exhausted I'd fall asleep. But in catching those planes and stopping them on a very short deck, they have this wire across, and that's what the illustration showing here. They have the hook, and it reaches down and grabs that steel cable, and that steel cable of a great deal of resistance brings that plane to a stop, okay? And I wasn't flying, but I rode in one flight that we landed on an aircraft carrier and were caught by the thing, and then another when they kicked us off, threw us off with a catapult. It was sort of exciting, but I wouldn't want to do it for a living. Problem set 8.4. Any of the odd number exercises there, 1 through 13, can be done. Okay? Now let's see the next thing here. Wait, I think let's see. I don't want to do either one. Let me go back to it. It talks about alternative energy sources, okay? And I'm not going to do a lot because there's really no problems here, but what we mean usually by alternative energy sources are non-fossil fuels, okay? Because fossil fuels are dirty, they're limited, there's only so much fossil fuel out there, and we're using it at an alarmingly rapid pace. So the alternative energies are others. One is hydroelectric. We've had that for years. In fact, we've dammed up most of the dammable rivers in the state and in the country where you can afford to do it. And then you get the falling water, the kinetic energy of the water turns the turbines. That makes electrical energy that is then piped out or sent out on the grid to all these places. We've used just about all the easily dammable rivers that we've got. Those rivers in low-lying, flooded, flat areas, you can't dam them up. They'd flood huge areas of land, where it's flat. You have to dam rivers that have a lot of fall to them, and usually in places that aren't very well populated. Well, as soon as Alabama Power, Southern Company started damming all these rivers and making these lakes, people started putting houses on the lakes and on the rivers and stuff. And now with the houses there, it's a lot harder to dam them up anymore because people value the property.
Can I ask you a question?
Yeah.
And I don't know if it's exactly related, but this week during the coverage on Hurricane Florence,
Yeah.
I heard at one point that the storm is picking up energy.
Uh-huh.
And I thought, like, made me think, like, oh, energy, what kind of energy is that?
Yeah.
So I was curious, like, were they just saying energy in a sort of ambiguous term, or
Okay.
what kind of energy does this hurricane pick
Right.
up?
Okay. When they're out at sea, especially over very warm waters, they're picking up heat energy, and that increases the wind speed, the rotation, the pressure drop, and those kind of things. But that happens. Say again? That's thermal energy being converted into kinetic energy. Yeah. Now, this week, Florence hasn't been gaining any energy. It's actually been losing energy. But what I'm thinking they might have meant was it picked up speed, which would be kinetic energy. Okay?
That's velocity?
That would be velocity. Yes,
And
exactly.
how does it pick up?
Okay.
Like, how
Well,
does that happen?
what happened there, and I heard today it was out over the Atlantic, the remnants of it. And what happens, you see, this is a very interesting question. I'm going to try to do this in somewhat of an orderly fashion.
So did they mean energy in the term of a physics energy?
I think they really meant speed, but that does influence kinetic energy, but it's not the kinetic energy of the wind as of the whole storm. Let me just draw your globe here for you, and that's a pretty lousy globe. And in here are called the tropics, the equator right in the middle, and you have the tropics there. That's very, very warm, okay? And our globe spins in a certain direction, and as such, in the tropics, pretty much, the wind usually blows east to west, okay? We live in the temperate area. Up here is the polar region. We don't even want to mess with that. This is the temperate area. Because we're spinning like this, we sort of drag our atmosphere with us, but that's why the winds blow east to west, because the earth spins faster than the air. So around the middle, that fat part around the equator, the tropics, the wind tend to go that way. In the temperate areas, because the globe isn't turning as fast, but the atmosphere has been drug around, we typically have west or easterly. We call them the prevailing westerlies. And if you look at the weather map, always what the weather is on the west coast, we're probably going to get that in a few days. What we get here in Alabama, my brother says we'll get the next day in Georgia. You know, when we talk on the phone, oh, you got rain? Well, we may get rain tomorrow then. You know, it's our typical pattern in here is this. Well, the hurricanes come from the tropical area, so they typically move east to west. And sure enough, that's where Florence came from. But once she gets up here in the tropical, you start hitting the winds coming from this way. So what happened, it came in and then slowed down because it was hitting the things, and it slowed down right over North and South Carolina and just dumped rain and dumped rain and dumped rain.
So
Every bit.
it loses momentum.
Yeah, basically that. It's velocity forward like that, moving in this direction slowed. But the energy it was losing, all that heat that it absorbed in the tropical area, it was losing it. It was, that moisture was coming out, and, so it was actually losing energy there. But what happened, it stalled, and then it started flowing back this way. So the motion of the storm was picking up energy, in other words, going back to sea. And that's why it's over the Atlantic now. It's not over any landmass, because it got picked up by the prevailing westerly winds and blown back out to sea.
Is that kinetic energy then? When it
Yeah, the motion going back to sea then picked up some, but that was minuscule compared to what it was losing with the rainfall, because it went from a hurricane to a tropical storm to a tropical depression to just a storm, and then it got blown back. And that's why it didn't have enough energy to resist these prevailing westerlies, and it blew them back. But it did, in a sense, gain energy in that it went from zero motion to motion back to the other direction. I think it was a poor choice of words, but that's
Well, I just wondered.
somewhat correct.
Like, I wondered, did they really mean energy?
Yeah, they probably didn't. They meant speed. People use energy for all sorts of things. In fact, I have students, when they're talking about energy, they'll say power. No, those are different things. You know, we talked about those. Power is the time rate of change of energy, just like force is the time rate of change of momentum. All these are time rate of changes. Okay. Now, was I going to say anything else? Alternative energies, we have hydroelectric. Now we've started using wind energy. Now, they used wind energy in the past. I mean, what do you think of when you think of the Netherlands? The windmills. They've always had them there, pumping the seawater, because they're below sea level, pumping the seawater back behind the dikes and the dams and the other things they have, because they're our country. They've made their country bigger by taking up sea space. Okay? The first farm that, when we moved down to Georgia from North Carolina when I was 4 years old, they had a windmill. It wasn't really operating well. That's how they pumped water to the cattle that were in the pasture behind where we lived. Okay? They didn't pipe electricity down there. They used the windmill to pump the water out of the ground. Okay? It wasn't working anymore. Electricity got easy to do, so we ran a well down there. So that was taken care of. But nowadays, they found out wind is very usable, and the picture here in the text is what they call a wind farm, a whole bunch of wind turbines. And my wife had professional meetings a couple summers ago in Park City, Utah, which is near Salt Lake City, and we had a whole week, so we went out and we went to Yellowstone and Tetons for a day or two, and then drove around and saw some of the states we don't usually see, like Montana and Idaho, because they're all right there near each other. And when we were driving through that, and parts of Wyoming too, we saw huge wind farms, because the wind's always blowing, wide open territory, and underneath the wind farms, the farmers were baling hay and planting crops and stuff, because the wind turbines are way up there. They can operate their equipment without any risk at all of getting hit. So they were leasing it out and still having their farm. So I thought that was really good use of land and resources. Okay? Another thing that they do, and they mentioned geothermal energy. Not many places can do this, but Iceland is one. As cold as it is in Iceland, and the name indicates it's pretty cold, they don't use any electricity to heat their homes. Almost zero. What they do, they're on a volcanic island, so they drill down close to, in the volcanic rock where it's pretty close to the magma, and it's really hot. They pump water down there and then pump it back up and send it through the streets, under the streets, you know, into people's homes, and all their floors are heated by hot water off of geothermal. No one's.
Now, does that, I don't know how to ask this question, but does that have to happen instantaneously, or can that be stored? Like when you were talking about the wind turbines that you all
Yeah.
saw, is there a way in which to store that energy and
Yeah.
save it? Like
Yeah.
we're talking about conserve, or does it have to be happening
Okay.
as the wind's moving,
Okay.
the activity has to
Okay. Yeah, that's going to be a more pertinent question than the next thing we talk about, but it's still important there. Any that, like if you have a very windy day, but it's moderate temperature and not many people are using, you can store, and this has been a big area of research and improvement in the last few decades, is batteries. You can store it in batteries and then bring it back out of batteries again. That's not a super efficient process, but it can be done. So they do tend to do that with batteries. And we're getting much better at our battery technology, so we're much better at that. The trouble with wind turbines in doing that is anything that's turning, the hydroelectric, steam power plants, anything, that's always AC coming out of it. Batteries are DC, so you have a little bit of loss when you have to convert from one to another and then back again. Okay, that's one problem. But solar energy, and they showed a picture here of a house that's actually a garage, and the whole I bet you south-facing roof of that garage is completely covered with solar panels. Now, solar panels produce DC, direct current, and those are very easy to store in batteries because guess what? Solar panels only create energy during daylight because they're based on the sun. So they do store theirs in batteries and then retrieve that, say in nighttime when it's really cold and stuff, to retrieve it back from the battery to use it to operate heaters and stuff. So it's all a pretty complicated setup because you're going some DC, some AC, and you have to go back and forth. But you see, I'm doing that right now. That's AC coming out of the wall. This is DC going in my computer. So I can do it, but if you feel this, it's warm. That means it's had some heat loss in doing that conversion. Okay? Those always are warm after you've been using them. Okay? Indicating that. And that's really all we had. There's a physics connection on wind energy and wind turbine technicians. You can read that if you'd like. It's just sort of an interesting set of rules. But then back to your point, okay, we have the same problems with hydroelectric. Sometimes you don't have high usage area, and what they'll sometimes do is take some of the energy they're producing, pump the water back up into the reservoir so they can use it again. If they're not using all the energy, if there's not a demand out there for the energy they're producing, what do you do with it? Well, they pump the water back up, and that gives the water potential energy again so you can convert it to kinetic. So they do that, okay? On the grid, it's hard to take a power plant offline. So they try to moderate, and they'll send energy like times when the south is at moderate temperatures, but it's already getting cold up north. We'll ship energy up there. But then in the wintertime, when we need the energy, we don't do as much. Or in the summer, when we need more, they're cool up there, they may ship some down to us, through the power line. So they try to balance the load. The wind energy is easier to balance because you can move it around like that. It's already AC, move it to where you need it.
How would you define energy again? Could you just define energy again?
Okay, energy is it's the ability to do work. Okay, so all your electrical energy production is any turbine, which would be water turbine, wind turbine, any kind of turbine, is producing alternating current, and any direct current would be, say, your solar, your batteries, and things like that. So, and all that is energy, but this is heat energy that's being lost. Any times you do conversions, you tend to have a bit of that. All right, that's the end of the chapter. There's a glossary at the end, and there's some formulas at the end, and there's a bunch of review questions. Now, the review questions are more conceptual, and they're usually, some of them are multiple choice, and some of them are just conceptual things. The ones that you probably are more focused on are your review problems, and all your review, not just the odds, all the review problems have answers in the back. So you can do any of those 15, and that would be pretty good. Your applied concepts was that roller coaster. If you want to do that one, it's certainly a lot of fun to deal with. But then they have a couple others. I see a Navy jet fighter is going to be going into an aircraft carrier, hydroelectric dam. They're pretty much applied problems. Okay, now that finishes Chapter 8, which means we're ready for Test 2. And I have some of these run off. I forgot to check to see if I had enough. I just have separated my Test 1s. Didn't mean to do that. They should stay here. I'm going to put them here, I think. Maybe I won't lose them that way. All right. Still, a few people haven't turned in Test 1, so if you haven't, please get those in. I did run off some of the test twos, and let's get those now. If I need more, the office is open. I can make more copies. I think the last time the copy ran out of toner or something like that. So here's your test two. Sorry, it's a little wrinkled. Test two. Oh, we got even swap, huh? All right, good deal. All right. Test two. Test two. That's two. Exactly the right number. Nope, I got one more. Got a couple more. Okay. Now let me make, in fact, I got a bunch more. I don't know how I wound up with so many extras of these. Let's make sure everybody did get the first question. Find the work done. Right? Okay, that's the right one. Okay. Let me see if there's any errors I can recall on this one. I don't remember any, but let me look. Okay, I've got to go through and yeah, I think all these are fine. I don't see any that had any glaring mistypes. Okay. So you have at least 2 weeks to turn that in. If you want to get it to me sooner, you can. You have next week to ask questions if you want to. You can ask questions anytime, but okay.
Are you going to be strict on like rounding and stuff like that?
Second?
Strict with rounding, like.
Yeah, I'm not strict with that, no. I'll just make the corrections. If you've rounded wrong, I'll show you where you did it right. But if you're right ballpark, you get credit. Yeah. Okay, so don't sweat that, but try to round correctly. Just keeps me, look, make my life as easy as possible. That's your job, right? Make all A's so I don't have to, it's so much easier to grade a 100-point paper than it is a 75 because I have to find all the errors and see where you made them and stuff. So get them all right and that make my job easy, okay? That's your purpose in life. Okay. Now, where do we go from here? I believe the next is chapter 12, is it not? Let me think. We've done 8. We go to 12. Okay? Oh my goodness, it can't be. Yeah. We were just beginning to have fun. Oh, we always have fun. Okay, chapter 12, matter, that's where we'll begin next time. Okay? Well, that actually, I planned it that way so we'd finish the chapter right at the end of the hour. Okay, 2 hours. Okay. We'll begin next time with chapter 12. Okay. I think chapter 12 will go a little bit faster than the other two have. The first one was really, I thought, sort of slow, but this one moved along a little bit better.